I'll begin with a word of prayer. All right, I'll start. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray be with us today, guide our work, Lord. In Him I pray. Amen. So I'm going to entertain a slightly applied question for the first couple minutes. And so the question was this, if, as I understand it, we're given a rocket that somehow is set up so that it will fly a figure eight. Is that right? Like this?
Yeah.
Or should I draw it like this?
Yeah.
Okay. Anyway, so this rocket would fly a figure eight in the absence of anything else. Without gravity being around, it would fly this figure eight, right? This is correct?
Yes.
So then the question is, how would you then, how would that figure eight motion be modified in the presence of gravity? So the way I would try to solve this problem would be with Newton's second equation. I would say that the mass, first of all, I would assume that the mass of the rocket doesn't change that much.
Correct.
Because otherwise it's more complicated, and then you'd have to pay. Then you'd have to pay me money. So I'm going to assume that the mass is essentially fixed, but that's a lie. And then, so the question is, what kind of gravity do I want to use? I got options, right? Because the force of gravity, I mean, in truth, is what? It's minus g m over, the radius of the Earth plus the altitude, let's say y squared, right? And that's, let's say y hat. I mean, if I'm setting up my system of coordinates here, like this, then this is maybe x, this is y, right? And you're assuming that the motion is in a plane, a vertical plane, so I can neglect the third dimension, and then this is not the scale, radius of the Earth, So if this motion is big, then I need to use this for the force because the force is variable. But of course, this is approximately minus mg y hat if you're sufficiently close to the surface of the Earth, right? And you can decide how bad an approximation is that in terms of what kind of altitudes are involved. Certainly, if your figure eight is just like 1,000 meters or something, then mg will do just fine, right? So I don't know. That depends. But then here, so what you got is this is, I don't know what that is. You guys, that's up to you guys, you engineers. You built this rocket, so I'll let you figure out the formula for that. But here we have d squared x dt squared, yeah, comma d squared y dt squared. This rocket force, the first part, the second part, right, the y component, the x component. And then force of gravity, well, that's a little bit easier here. It's got no x component. And the y component is, well, F gravity. And so scratch the y hat just for the sake of discussion here. So that's just the y coordinate of the gravity force. I mean, technically, this is the real force of gravity. Dot y hat is this, yeah. So I don't know, maybe I should use a sub 2 or something to be not getting into trouble with your physics professor. So you got to solve equations, right? You've got d squared x dt squared times the mass of the rocket is equal to the force, the rocket boost, the thrust force of the rocket. That's your x equation. Your y equation, d squared y dt squared, would be the y thrust of the rocket. And then, the simplest thing would be just minus mg, yeah? I assume that the rocket thrust is pre-programmed to make this figure eight.
Yes.
In the absence of gravity.
Yes.
So that's a given for you guys. And you could try to solve those numerically at least. But of course your FR1 and FR2 are somewhat complicated functions of time. But yeah, you could attempt to solve this. Of course, the more interesting one would be, instead of that, minus, well, g m, big M, over the radius of the Earth plus y squared. I mean, you could do that. You could try to solve that. Now, that would be more complicated because that would be a nonlinear system of differential equations, because here your dependent variable's y, and you've got a 1 over y squared. So to actually solve that is, like, to explicitly solve that, that's quite a feat. With little mg there, that's a linear system of differential equations, non-homogeneous, because your rocket thrust is a function of time. But we actually have the tools to solve that kind of problem for given rocket thrust in about a week here. Yeah. Does that help?
Yes.
Okay. So anyway, not irrelevant to your course, here's a real-world example, although somewhat strange, that illustrates differential equations come up in solving equations of motion. I mean, Newton's second law, ma equals to net force, is what? It's a system of second derivatives equal to forces. And if those forces depend on position, then that's actually a system of second-order differential equations. Ordinary differential equations, we can try to solve them. Here, let's look at one we can actually solve. How about this? What if I try to solve x prime equals to y minus y, and y prime equals to x? Let's try to solve this system of differential equations. Now, we talked about the general theory last time before we had that in-class activity last time. Sorry, I still haven't finished assessing your in-class activity. I fell asleep last night. Sorry about that. And then these annoying Calculus 2 students, they're asking me questions in office hours. Apparently they want to learn calculus. So annoying. But we'll forgive them. So we talked about the general theory of this already a little bit, right? So we know that solutions exist. We know that the sum of solutions is a solution to a homogeneous problem. But what we don't yet know is how to find fundamental solutions. That's what I want to talk about today. I'm going to take my time getting there. First of all, I want to show you some ad hoc methods, all right, and some general ideas. So ad hoc in the sense that, like, we're just going to use, how do you solve systems of linear equations in high school? One of the methods you're taught is just elimination, right? Take one equation, you plug it into the other, you keep reducing the number of variables until you got one equation, one unknown. You solve that thing, then you plug it back up into your previous equations and kind of work your way back up until you got solutions to all of your equations, right? This is elimination. You can do the same thing for differential equations. Like I can get rid of x up here by saying, well, x is equal to y prime, right? So that implies that x prime is actually equal to y prime prime, which is equal to minus y, right? So I'm just plugging the second equation. Let me call this 1. Let me call this 2. So what I did was I took 1, right? And I substituted it into 2, essentially, to get this. And that is something we already know how to solve, right? We got y prime prime plus y equals to 0. So, great. This gives me y is equal to c1 cosine t plus c2 sine t. Many of you know how to do this. Some of you don't. See here. Maybe some of you know this one. It's just one on the test I had, that exponential piece, which was clouding your judgment. Anyway, let's say we all know this. We're comfortable with what I just did. Once we have that, how do we get x? Well, x is y prime, right? So to get x, you just go back to equation 1. So x is equal to minus c1 sine t plus c2 cosine t. And, you know, if you wanted to pick a point, say P1, P2, you know, and find the solution that goes through P1, P2, say you want to make the point P1, P2 be reached at time 0, for the sake of discussion, what C1 and C2 should you choose to find the solution that goes through here? So suppose that that's equal to x of 0, comma y of 0. What would that make C1 and C2 equal to? Plug in 0 into this, what do you get for x? We get C2, right? Plug in 0 into the formula for y, what do you get? C1, right? So apparently, C1 is equal to P2, and C2 is equal to P1. So to get the curve, the solution, which goes through the point P1, P2, which I'll draw like this, the formula is what? It's x is equal to, I just said C1 is P2, so minus P2 sine t plus P1 cosine t, and y is equal to P2 cosine t plus P1 sine t. There you go. That's the solution to this initial value problem. I'm assuming initial values, x of 0 is P1, y of 0 is P2. It's a circle that goes through that point, right? Unless P1 and P2 are both 0, in which case we have the 0 solution. So this differential equation has solutions which are circles, right? In fact, if you chose different initial points, you'd get circles. By the way, this has a connection with integral curves. If we look at the vector field f, right, equals to minus y comma x, right? And you want the vector field which lines up, you want curves which line up with this vector field, which means that you want f of the curve, let's say, need a language here, how about gamma? Gamma of t equal to d gamma dt. So this would make gamma an integral curve, curve to f. So if you look at this, what this condition says, it says that if gamma is equal to, say, x of t comma y of t, right? What's f of gamma of t? Well, it's minus y of t comma x of t. That's my f of x comma y of t, right? And on the other hand, I've got the velocity of the curve, of the path. So that's, ddt of x of t comma y of t, which of course we do component-wise, right? That's dx dt dy dt. And so you see, to find the integral curve to this vector field f, I have to solve a pair of differential equations. I have to solve the differential equations dx dt equals to minus y and dy dt equals to x, equating the x and y components of that condition I just wrote down. So my point to you guys is that this is an interesting problem to find integral curves to vector fields. Why is it? I mean, I talked to you about this before, but if the vector field has for example, if the vector field is the velocity curve, if you have some sort of like static fluid distribution and you have the f has the meaning of velocity of the fluid, then the integral curves are actually, if you put a dot of ink into the water, then that's the line that dot's going to trace out. It's the flow line. The integral curves are the flow lines of the velocity field, for example. Or if the vector field is an electric field, it's the path that a little positive point charge is going to travel after you drop it in this electric field. The electric field will push it along its flow line. Or if it's gravity, if it's mass, then it'll go the opposite direction because gravity is attractive, so it's harder. We don't think about pushing, think about pulling. It'll pull it along if the force of gravity goes that way, then the mass, I guess the mass gets points pushed that way. Never mind. I'm an idiot. Sorry. Anyway, so my point is, by solving this system of differential equations, we actually just found the integral curve to this vector field, right? What's the difference between this and your test problem? On the test, you wouldn't have done this, right? We didn't know this on the test. What did we know on the test? How we would have found the integral curves? We would have solved what? Almost on board with you. We would have solved x dx plus y dy. We would have solved this Pfaffian form differential equation. Timeless, right? So what's the difference? Oh, here I'm finding parametric curves, right? Functions of time which parameterize the integral curves. This just gives me straight up an xy equation for the integral curve. It doesn't give me a sense of direction, though. These will actually line up with the vector field in the same sense. This gives me a disoriented version of the integral curve. I mean, this straight up is d of 1/2 x squared plus 1/2 y squared, of course. So the integral curves from this way of thinking are circles, right? I mean, clearly this constant's 1/2 r squared, right? But, I mean, that's the solution to this. It's 1/2 x squared plus 1/2 y squared. Scratch the halves, right? I mean, the solution is this. But then that solution doesn't give you any sense of, is it clockwise or is it counterclockwise, right? And actually that matters for integral curves. So I gave you a slightly substandard version of integral curves for test 1. You know? Because technically speaking, this isn't clockwise or counterclockwise, right? It's just a circle. But these have an orientation. So that's an improvement. But anyway. All right, enough about it. I'm telling you a little bit about why we're interested in systems of differential equations is because they come up in interesting applied problems. Integral curves, Newton's equations. How do you solve them? Well, this is kind of depressing that we're just going to do substitution, like, yeah, what is it? Uh-oh. I'm imagining the direction, yes. If I multiply this by minus, it will basically replace t with minus t in these equations. Okay, so this is going to be a tough method for more complicated differential equations, right? Like, what about this one? What if I had, you know, x prime prime equals to minus 3x prime plus 3y prime, and then I have like y prime prime is equal to minus 2x plus y prime, and I want to solve that system. I'll just tell you, I don't, all right? I just don't want to solve that using our current method. It would be a pain. It would eat up a lot of my time in here. But what I would like to show you is that we can recast this problem. So method of example 1, tiresome. This may always be a tiresome problem. I mean, I guess I could try. Oh, I'm wrong. Actually, this wouldn't be that bad, because I can solve the second one for x, right? And if I can solve it for x, then I can plug that into the first equation, which just gives me a second order, it gives me a differential equation in y, right? So, possible, but uninteresting. Uninteresting because it's not the general path that we're going to go down. I mean, this is a way you can solve them. But I want to show you another way. So what I want to show you is that we can actually recast this as first order problem. So this system of two differential equations, two second order differential equations, I can actually recast it as 4 first order differential equations using what's called reduction of order. So what we're going to do is we're going to say x1 is x. We'll say x2 is x prime. We'll say x3 is y. We'll say x4 is y prime. And if we play this game, we can replace these two second-order problems with a corresponding system of 4 first-order differential equations. Excuse me. So let's see here. What's this first, x2 equals x prime? What's that say? That says that x1 prime equals to what? x2, right. And let's see here. What is x2 prime is what? That's x prime prime, right? Now x prime prime by equation 1 is what? Let me call this equation 1 here. So using equation 1, I'm going to translate that into my new variables. X prime is what? Oh, so you say minus 3x2. Okay. And then what? Plus 3x4. Very good. See what he's doing? Do you guys understand? Do you follow? We're translating the underlined red thing in terms of our new variables. This is called reduction of order. How about x3 prime? Right, that's because that's y prime, which is x4. x4 prime. I'm going to need to use equation 2 now. Let's see here. What did Mr. Wynn tell me? Minus 2x1 and plus what? Oh, plus x4. Okay. So we started with 2 second-order linear homogeneous differential equations. And after reduction of order, now we have what? We have a corresponding system of 4 first-order differential equations. And I can rewrite them as a matrix problem like as follows. This is x1, x2, x3, x4 prime equals to, my matrix is going to be a 4 by 4 matrix. So to get the first column, excuse me, first row, I'm an idiot. I look at the first equation. I get 0, 1, 0, 0. That's my x1 prime equation. The next one, I have 0, 0 minus 3, 0, 3, okay. The next one, x prime, so that's 0, 0, 0, 1. And then finally, minus 2, 0, 0, 1. Now, given that, I can use technology to find things about the coefficient matrix that will tell me what the solution looks like. Now, we haven't developed those tools yet, but I'll try to come back and use those tools on this matrix. All right, and we'll see how it goes. I may regret it. It may be outside my scope of what I want to cover today, because I just made this problem up. I mean, it could be that this needs complex solutions, which I don't really want to talk about today. Oops, I think I already did. See, this sine cosine thing, it's not going to be covered by the method I'm going to build today. Yeah. Until we complexify the method next day. Yeah. I'm sorry, it's kind of like a broken record in here. It's always the same stupid thing. I build some real technique. It doesn't get everything. Then we complexify it. We get the complex piece. But now there's a wrinkle. Even so, there will still be pieces which are left out. Then we'll have to talk about something a little bit deeper in terms of linear algebra. So, linear algebra. I should spend about 10 minutes talking to you guys about linear algebra before we go any further. So how many of you have had or are taking 221? How many people have not taken 221? How many people have not taken 221 and did not do linear algebra at all in high school? Oh, sorry, you guys. You guys are in a bad place. It's because there is some expectation that linear algebra, and I don't mean the full linear algebra. When I say linear algebra, I mean you've looked at a matrix, you've calculated a determinant, you've done row operations, no? A little bit. All right, so I'm going to try to fill in some of those gaps for you right now. But so just getting back to, basic linear algebra. And even those who are in linear algebra could use a review, so it's okay. You won't object. So the basic problem of linear algebra is solving, say, n equations and n unknowns. Now, actually, this is already a simplification because in 221, you'll deal with n you'll have n, this be m and that one be n, right? You'll deal with like 3 equations and 2 unknowns and other stuff like that, right? I mean, I do when I teach 321. We don't just do 3 equations and 3 unknowns. We'll do 5 equations and 7 unknowns or whatever. So this is already a simplification because this forces when we look at the equation, something like a11 x1 plus a1n xn, an1 x1, ann xn. When we look at this, b1 through bn, so n equations and n unknowns, it's already a simplification because you see I can write the matrix as a what's called square matrix. Right? So if we have an unequal number of equations and unknowns, then the coefficient matrix is not square, it's rectangular, and lots of things are known, but they're not as simple as what I'm about to tell you here. So this is the nicest case. When we have the same number of equations as unknowns, we get a square coefficient matrix. This is the n by n coefficient matrix. So how do you solve this problem? Here's the big idea. So first of all, we use some kind of compact notation for this. Instead of writing all this, we instead say, what we're looking at is matrix A, right, times, say, vector x equals to vector b. So this is the matrix notation, matrix column notation, which is a great simplification in writing, right? So A is the coefficient matrix, B is the so-called inhomogeneous term. If B is equal to 0, then what? Terminology. B equals to 0. This is a homogeneous linear system. If B is not equal to 0, it's non-homogeneous. Does this sound familiar? It should, right? We use the same terminology in differential equations. The difference, of course, is when we're solving linear equations, what's our solution? It's a point, or it's a set of points, right? What's our solution in differential equations? It's a function, right? Or it's a set of functions. So, it's a different game we're playing, but some of the terminology is related. So how do you solve a system of n linear equations and n unknowns? Well, if you have technology, number one is you identify A and B, and then you form the augmented coefficient matrix, which is this. And then what do? use technology, right, to calculate the reduced row echelon form of your augmented coefficient matrix, or the RIF. In step 3, read off the answer. Interpret data from 2 to write answer. Now, if you don't have technology, what does this look like? If you don't have technology, you actually have to calculate the reduced row echelon form by hand. And we do this by row operations. Row swaps, row additions, row rescalings, right? Okay. I'll do some of that for specific examples relevant to this course when we get there, all right? I'm not going to do them right now because it won't connect to the actual problems we're solving in here. I'm going to wait for those details till we get to actually those problems in the context of differential equations. But I need to give you this big picture speech so you appreciate what I'm going to say for differential equations, all right? Answer. What does an answer look like for a system of linear equations? There are 2 kinds of answers. You either have no solution, right? You have a unique solution, right? Or you have infinitely many solutions. These are the 3 kinds of answers you get. No solutions, unique solution, infinitely many solutions. You can already see these 3 possibilities if you think about the 2-dimensional case. What are 2 equations and 2 unknowns? No solution would be like parallel lines. These are 2 equations. The graph represent 2 equations and 2 unknowns. Parallel lines never intersect, no solution. Unique solution, skew lines. Unique solution. Infinitely many solutions is when you have the same, same line. So this one would be something like, here you got x plus y equals to 1, x plus y equals to 2. No solutions. You can't have x plus y equal to 1 and x plus y equal to 2. It's impossible. This one, pretty much anything. X minus y equals to 7, x plus 3y equals to 2. That'll have a unique solution. This right here would be something stupid, like x plus y equals to 0, and 2x plus 2y equals to 0. 2 equations, 2 unknowns, 3 examples. Those are the 3 cases. This continues to be true over the real numbers for n equations and n unknowns. There are always 3 cases. No solutions, a unique solution, right? Or infinitely many solutions. Them's the possibilities. You're like, you mean you can't have a system of linear equations where you just have 2 solutions? No, that does not happen for linear equations. It's not like the quadratic equation. Now, something wonderful happens. There's a tool. So what's the matrix of the coefficient matrix in each one of these cases I can write down with a minimum of effort? The coefficient matrix here, 1, 1, 1, 1. Coefficient matrix here, 1, minus 1, 1, 3. Right? Coefficient matrix over here, 1, 1, 2, 2. So there's my 3 coefficient matrices. You can calculate the determinant. You guys know how to calculate determinants from calculus 3 because that's the pattern for the cross product, right? We use it as a mnemonic there, but well, you've done some of this already because we talked about the Wronskian, didn't we? So you calculate these determinants for me. What do you get? We get 0, 4, 0. Yeah. So this is the theorem. Ax equals to b has unique solution if and only if the determinant of A is not equal to 0. So we can tell whether or not our linear system has just one solution by just checking if the determinant is non-zero. If the determinant's non-zero, then there's a unique solution. In fact, we can find the inverse matrix in that case, but whatever. Now, how about this? What if we're dealing with the homogeneous? Let's talk about the homogeneous problem for a second. Homogeneous case is AX equals to 0. Does this have a solution? What is it? No, you know. What can I multiply by a matrix? What vector can I multiply by a matrix? What can I make x equal to so that I automatically get 0 there? 0, right. Notice that a times 0, the 0 vector, is equal to 0 again. I guess I should have 0 vector here. I forget 0 vector, whatever. The point is, a homogeneous problem always has one solution, the 0 solution, right? So what does it mean then if the determinant of A is equal to 0, then what? Fill in the blank. What does that force us to say about this homogeneous system? It has more than one solution, so it has infinitely many. So if we have a homogeneous problem, right, it's always got a solution. It's either got a unique solution or it's got infinitely many. Them's your choices. As it happens, the algebra problem that we'll be led to is almost always this case, that we're in the homogeneous case and there are infinitely many solutions. And those infinitely many solutions we call eigenvectors. In fact, 0 is the one thing that's not an eigenvector in our context. All right, I think I've said enough about matrices and systems to confuse you. So my task is done. I have confused the students enough now. Now let me get back to actually what I will. There's really no, in good conscience, I can't really test you on this. I'm trying to provide a conceptual backdrop for what I'm about to do. Okay. In the past, I have spent a whole lecture actually working on linear algebra, and I don't think it's productive for you guys. I think it's better for us to spend more time on the actual systems of differential equations themselves. So that's what I'm trying to get to. Okay, finally, the problem. Sorry, I'm taking too long to get to this. So we're trying to solve dx dt equals to ax. We want to solve this where A is a constant matrix. I hope I've given you some evidence in my example 2 that this is actually going to allow us to even solve systems of higher order problems, because we can always take a higher order problem and we can do reduction of order and always boil it back down to this for a homogeneous problem. So this is more general than it at first appears. But here, A is an element of what I call our n by n. So it's a constant real n by n matrix. All right? So how can we solve that? So here's my educated guess. So let's set x equal to e to the lambda t u. All right, where lambda is a scalar. All right, it's a number. And u is constant vector. Let's see if that's enough to solve this differential equation. Can we solve star? Let me give it a name. Can we solve star using this guess? And how's that going to work? So we do what we always do. We make a guess, and then we plug it into the differential equation and see what it demands of us on the parameters that we've introduced. In this case, we've introduced a number lambda and a vector u. What's the nature of this number and vector if it has to solve star? So here we go. We need that d dt of e to the lambda t u, that should be equal to a times e to the lambda t u, right? We need this. Okay, so let's work on this. There's nothing much I can do to the right-hand side. But the left-hand side, I can differentiate, right? This gives me lambda e to the lambda t u equals to a e to the lambda t u. Notice that the differentiation of the constant vector is kind of boring. You just pull that out of the derivative. And derivative of e to the lambda t, well, we know that's lambda e to the lambda t. And this would still make sense if lambda was complex, but that's next time. So then e to lambda t, well, that's a non-zero function, right? So just divide both sides by it. What's this say? It says that lambda u is equal to au. Right? So this means that u is what's called an eigenvector with eigenvalue lambda for a. So, I mean, this right here is the definition of eigenvector u. Now we have to assume that u is not equal to 0, right? With eigenvalue lambda. Now, this, I don't actually like this form of it. It's more fun to do this. So we say that's really au minus lambda u equals to 0. And what we'll do is we'll rewrite that as a minus lambda I times u equals to 0. This is a more nice for calculation. For calculation, we look at it this way. So great, but then what? So we want to find u not equal to 0 such that a minus lambda I times u is equal to 0, right? Now, I need to come up with a different name for the matrix that's next to u so that we can talk about it. Yep.
Where did the I come from?
Oh, I is the identity matrix. I'm sorry, guys. So I is 1, 0, 0, 0, 0, 1. It's got ones down the diagonal. For example, in the 2 by 2 case, this I is just 1, 0, 0, 1. So let's look at the 2 by 2 case just for a second for those of you guys who have not seen these things before. So if I take the matrix 1, 0, 0, 1 and I multiply it by, like a times b, what do I get? I get a times 1, I get a times 1 plus b times 0, and I get b again. So matrix, so if I take the 3 by 3 identity matrix and I multiply it by ABC, it's going to give me back ABC. So this matrix I, it serves like the number 1 for matrix multiplication. It's a so-called identity matrix. It's a matrix which has zeros everywhere and just has ones down the diagonal. So lambda u, if you'll allow me this short manga-style calculation, sorry, manga-style, what am I saying? This is equal to lambda iu because u is equal to iu. So the reason I'm doing that is I want to rewrite it as a single matrix times a vector, all right? And so putting the I in there allows me to write this as a single matrix times the vector. And the advantage of that, right, is once we get to this, then if I think of this matrix being B, right? Look at this matrix B. What can we say about it? I'm looking at the equation BU equals to 0, right? Matrices don't work that way. Just because matrix times something is 0, that doesn't force the matrix to be 0. We don't have that kind of cancellation. Yeah. Well, right. Well, I mean, there's two cases, right? If the determinant of B is non-zero, what's the only solution to this equation? 0. This is a homogeneous equation, right? It's got 0 as a solution. So if I want infinitely many solutions to this equation, and you best believe I do, because if this solution is going to be interesting, what do we need for U? We want non-zero, right? We want non-zero U, because if U is 0, that's just the 0 solution. We don't need all this to find that 0 is the solution, and it's not useful to us. We're looking for non-zero solutions to form our linearly independent solution set, you know? So I've got, this homogeneous equation. I want it to have a non-zero solution. I already know it's got the 0 solution. There must be infinitely many solutions. In fact, I must have that the determinant of this is equal to 0. Because if I don't have that, then I don't have infinitely many solutions. This is really good news, because up till now, lambda's been this arbitrary parameter. We don't know what it is. But see, now you see that this lambda has to satisfy something. It has to satisfy this equation. The determinant of a minus lambda I is equal to 0. It must satisfy this equation. This definition is the characteristic equation. The solution to the characteristic equation are the eigenvalues. And the thing is that when you work out that equation, it's an nth order polynomial equation in lambda. So if we're working over the complexes, we always have n eigenvalues, possibly repeated. In the reals, it may or may not be the case that we have actually eigenvalues. All right. But now we have a method. Here's the method. So here's the method that I have justified here for you in part. Number 1, we find solutions to the determinant of a minus lambda I equals to 0. Number 2, we find the eigenvectors corresponding to those lambda. And then 3, you construct your eigensolutions. Eigensolutions as in x equals to e to the lambda tu. Those are going to be solutions. Here, let's actually work through one. Suppose we want to solve x prime equals to, let's see here, 2x plus y, and y prime equals to x minus something y. You got to give me a second here. I got to fill in the blank here, make it reasonable for us, all right? So fine. Let me put a variable here, if you don't mind. I'm going to put a c here, cy. There we go. So we've got xy prime equals to, sorry, in the best case scenario, I wouldn't have had so many questions in office hours. I had a chance to look up an example for class. Right now I'm making one, so you'll forgive me. Let's hear. But you can, yes. Oh, we'll come back to that. Yeah. Thank you for reminding me not to erase it. Yes. So this is my A. And you guys are going to help me choose a C so that the algebra works out nice. I want distinct real solutions to my characteristic equation. So we're looking at the determinant of A minus lambda I. So what that means is the determinant of 2, 1, 1. Why did I put a minus? Let me put plus C there. Sorry. Just C there. And then minus, what's the identity matrix? It's 1, 0, 0, 1. Okay, so what is that? That's the determinant of 2 minus lambda, 1, 1, C minus lambda. So let's see here. That's lambda minus 2 times lambda minus C minus 1. Yeah. This will be slightly unpleasant, but a kind of decent example. Let's put C equal to, unless you guys see a better idea, like I'm thinking C equals to minus 2. That at least gives me like lambda squared minus 5. But I'd like to have without roots. Can you guys tell me a C that'll give me integer solutions?
Without if you had plus 2, then you would have some difference. So you'd have minus squared minus 4 minus.
If I put, sorry guys, lambda squared minus 2 plus C, lambda plus 2C minus 1, maybe that'll help us in our quest for making C easy. C equal to what? Oh, so 2 is nice. Okay, so if we put C equals to 2, it's nice. I was scared off from that because I was worried about this, but oh, you're right. So plus 3, is that? Oh, yeah, that's, hey, perfect. Thank you. So I do lambda minus 1 times lambda minus 3. Hey, don't worry. You guys are not responsible for making up examples. The example will be given to you on the test. It's just up to you to solve it. So I'm this business with C. You can just, you know, I mean, there is a perverse kind of homework problem where you're asked to solve it with an arbitrary parameter in a spot, right? That's kind of an evil problem. So what I'm trying to tell you is just we're going to put C equals to 2 to make the problem nice. Is okay?
Yeah, we're fine.
Okay. Okay, so now that we got that out of our system, let's solve it. Again, my apologies for not having an example ready for you. So example 3 continued. We just figured out we want to put A equals to 2, 1, 2, 1, 1, 2. Is that right? I should have guessed that. And we figured out with that, if we calculate the determinant of A minus lambda I, that gives us lambda minus 1 times, I'm just summarizing what we just found, right? Is that right? Well,
Shouldn't the lambdas be on the right there? Shouldn't it be 2 minus lambda and C minus lambda?
yes. Why doesn't it matter, though? Because if I have A minus B times C minus D, that's equal to B minus A times D minus C. Well, the thing is, there's two minuses. I'm just minus times minus. And I just prefer to write lambdas first rather than minus lambdas in this step. But I hear you. Okay, so we have lambda 1 equals to 1, and lambda 2 equals to 3. These are my eigenvalues, right? Now I need to find the eigenvectors. So let's start with lambda 1 equals to 1. We need to look at A minus I times, let's say, U1 equals to 0. This is the equation I need to find solutions to. What is A minus I? It's 1, 1, 1, 1. And then I like to use like U and V for the components of the eigenvector. We really don't need any fancy schmancy linear algebra here. You can kind of just look at it and go, oh, hey, it's just like I said, it's like this case, except with U's and V's. Don't use X's and Y's for your eigenequations. It's a bad idea, because we use X, Y, and Z for the solutions to the differential equation. If you use X, Y, and Z for the eigenequations, bad things will happen to you. And it won't be of my doing. It'll be of your own doing, because it will confuse you. I've seen it many times. Too many times. Let's see here. U plus V equals to 0. So that means that U1 equals to what? It's equal to like U comma minus U, right? Because this says that V is equal to minus U, right? And then you can pull out the U. And any non-zero U will give you an eigenvector. There's infinitely many of them with eigenvalue 1. So I say set U equal to 1. I say choose, for my convenience, U1 equals to 1 minus 1. Es bueno. We got one more eigenvalue, right? 3. What's the eigenvector for eigenvalue 3? So lambda 2 equals to 3. Now we got to solve A minus 3I times U2 equals to 0. What's that actually look like? Well, that's minus 1, 1, 1 minus 1, UV equals to 0, 0. So again, it's the same equation, right? Pick either one you like. I'll pick the first one, minus U plus V equals to 0. That's my first equation. So that tells me that V is equal to U. So therefore, U2 is going to be, U comma U. I can factor out the U, and I've got U times 1 comma 1. So set U2 equals to 1, 1. That's a good choice for my eigenvector. If you want me to get technical, I am choosing a basis for the lambda equals to 3 eigenspace. And I chose a basis for the lambda equals 1 eigenspace. But all I'm saying is pick a specific vector, because we're going to make a solution with these vectors. You don't want to work with a family of vectors. Pick a specific one. Make your life easy. So if you've got a parameter, just set it to 1. Why not? Okay, in total then, yep.
How do you get the U and V equation?
So this